In this video, we are going to look into electron delocalization in organic compounds. To be able to study delocalized electrons, first we need to understand localized electrons. Localized electrons are electrons that belong to a particular bond or particular orbital. That means they are localized to a particular bond or particular orbital. Couple of examples of compounds that contain only localized electrons are dimethyl ether and propene. Each electron pair in this case can be assigned to a particular sigma or pi orbital, and there is no doubt to which orbital it belongs to, or it could be assigned to atomic orbital, in this case on oxygen of dimethyl ether. So it belongs to atomic orbital as free electron pair. A single electron could also be localized if it belongs to a particular orbital. That would be a free radical. Here is a more detailed example. So in case of methanol, we can assign every single electron pair either to oxygen, hydrogen, carbon, oxygen, or carbon-hydrogen bonds, or to orbitals on oxygen, to sp3 hybrid orbitals on oxygen. Those are two free electron pairs on oxygen. Delocalized electrons are electrons that do not belong to a particular atom or a bond. So that means that they are delocalized. And to explain delocalized electrons, we have to introduce new concept, a concept of resonance into valence bond theory. The localization of electrons is a physical phenomenon. We know that electrons are delocalized. Molecular orbital theory actually considers all electrons to be delocalized in its full form. But that description is too complex. On the other hand, valence bond theory considers all electrons to be localized. And in fact, we don't have very good valence bond formulas, those are Lewis structures, that can show compounds with delocalized electrons. But we know that electrons are delocalized. And so we are facing a problem. We have a very good theory that we like to use, valence bond theory, but it cannot explain actual observed physical phenomena, the localization of electrons. Now we have a choice. We can abandon the theory in favor of molecular orbital theory, but the problem is that molecular orbital description is too complex for use with larger molecules and even with smaller molecules. The alternative is to try to fix a broken theory. And we have introduced a fix, and that fix is resonance. So resonance is not actual physical phenomenon. Resonance is description of the actual physical phenomenon. Actual physical phenomenon is electron delocalization. Resonance is description, how we use valence bond theory to explain electron delocalization. Basically, it's a fix. So what we do is we represent a molecule such as methyl vinyl ether that exhibits electron delocalization as combination of individual Lewis structures. You will see more in next video how we come up with those structures, but in this case it's important to note that electron delocalization is shown by curved arrows. Unfortunately, that's the same convention as in case of a reaction. The difference is that in the case of a reaction, curved arrows indicate movement of electron in time. As reaction progresses, curved arrow indicate how electron pair or single electron moves. Here it's movement of electrons in space. They're always delocalized, and curved electrons show how they are delocalized in space, to which orbitals. And so these electrons here that are delocalized are one free electron from oxygen and pi electron pair from carbon-carbon double bond. So those two are delocalized and belong to more than one orbital. We have two extreme structures, one on the left and one on the right, and note the resonance arrow, this double-headed arrow, that's resonance arrow, and it shows that actual structure is neither of the two extreme Lewis structures, but combination of the two, somewhere in between the two, what we call resonance hybrid of those two individual resonance structures. We can maybe represent it as structure at the bottom. You can see it's combination of the two, so it shows that oxygen carries partial positive charge, terminal carbon partial negative, and that oxygen, carbon, and carbon-carbon bonds are partially double bonds. The problem is that this structure doesn't provide any more information compared to individual resonance structures and could even be confusing because with these dotted bonds, we don't know how many electrons are there. Is that one electron pair that is delocalized through that entire space, or are there two electron pairs? So for that reason, we prefer to draw resonance hybrid as a combination of individual, complete, proper Lewis structures. One analogy would be, if we try to explain concept of resonance, is if we try to explain what is a mule, then we can say that mule is resonance hybrid of horse and donkey. So that's what we get when we mix up horse and donkey. So it's not something that is part-time horse, part-time donkey. It's not equilibrium between horse and donkey. It's always a mule. But if you don't have a term for a mule, then we'll say, well, it's a combination of these two, horse and donkey. Or if you try to explain to somebody what is a green color, green dye, well, that's what you get when you mix blue and yellow. And so if something is green, it's always green. It has its particular property of being green dye. It doesn't flicker between blue and yellow. It's not at equilibrium between blue and yellow. It's always green, but simply we are using, if we didn't have word green, then this is what you would say. You would say it's a combination of blue and yellow. Simplest species with delocalized electrons are various allylic species, allyl cation, allyl radical, and allyl anion. And we are going to now examine valence bond and molecular orbital description of each. Valence bond description is shown here. So for each of those, allyl cation, allyl radical, and allyl anion, we have two resonance structures. For allyl cation, we can see that pi electron pair is delocalized into the empty orbital of the cation. And so we have two extreme resonance structures. Actual structure is combination somewhere in between the two, where positive charge is shared by carbons 1 and 3, and all the bonds are partial double bonds. With a free radical, of course, then that free electron is partially delocalized between carbons 1 and 3, and note how we use half arrows to indicate electron delocalization. Finally, in case of anion, free electron pair moves to form, or is delocalized, it's not really movement in time, it's delocalized to form new carbon-carbon double bond, and pi electron pair ends up on the far carbon to form new free electron pair. So we can see that free electron pair is actually delocalized on carbons 1 and 3, and each bond is a partial double bond. Since in each case we have two equivalent resonance structures, valence bond theory would predict that all three of these species are equally stable. Here is molecular orbital description. So we represent pi orbitals, and in each case, since we have three atoms, where each atom contributes one atomic p orbital for formation of molecular orbitals, three molecular pi orbitals are formed. And there are actually pi orbital as bonding, n non-bonding, and pi star anti-bonding. And you can see their energy levels are as shown. So they are filled from the lowest energy pi orbital all the way up to anti-bonding. There are no electrons to fit actually into anti-bonding, as you will see. So for allyl cation, there are only two electrons. We start with three carbon atoms that contribute one atomic p orbital with one electron each. So we start with three electrons, but since this is carbocation, one electron is lost. There are two left. Following Aufbau principle, we place that electron pair into lowest energy orbital, and that's the molecular orbital structure of allyl cation. Bond order is number of bonding minus anti-bonding electrons divided by 2. And so that's 2 minus 0 divided by 2, 1. That shows that bond order is 1. Or in valence bond theory, you would say that there is one pi bond present. For allyl radical, we have that third electron, but that third electron fits into non-bonding orbital. Non-bonding orbitals don't count. Electrons in non-bonding orbitals don't count when counting bond order, because they neither strengthen nor weaken a bond. They are those free electrons in atomic orbitals if you look at valence bond theory. So again, bond order is 1. And for allyl anion, we have additional electron. Anion means that species has gained an additional electron. So we have 4 electrons. One electron pair belongs to pi orbital, next fits into non-bonding orbital. Again, non-bonding doesn't count. So again, bond order is 1. So according to valence bond, according to molecular orbital theory, all three of these species, allyl cation, allyl radical, and allyl anion, all of them have same bond order of 1. And that means they are all equally stable. So in this case, both theories provide equal prediction, or same prediction, that both valence bond theory and molecular orbital theory predict that all three species will be equally stable. And that's indeed what has been observed. To find which theory is better, which one is more accurate, we would need to come up with examples where they provide different predictions. And you will encounter that later in the course, and you will see that it is the molecular orbital theory that provides correct prediction and not a valence bond theory. The most studied and the best known compound with delocalized electrons is benzene, and this is formula of benzene. Now, benzene is usually represented as 1,3,5 cyclohexatriene, but it is not. The electrons in 3 pi double bonds are delocalized. In the older literature, in the 50s and 60s, maybe even as late as 70s, it was represented like this, as closed loop of delocalized pi electrons. You should be familiar with this formula. You should know what it means. That's old formula for benzene, and it's not the only one, but we have abandoned it. And the reason why we abandon it is that it's not always clear how many electrons are represented. So look at these two structures, structures 1 and 2. One is structure of naphthalene. If each ring represents closed loop of 6 pi electrons, then we would say naphthalene has 12, but it actually has 10. So this could be deceptive. And 2 is actually non-existent compound. But using these closed loops, we could actually end up drawing non-existent compounds. So that's not the proper Lewis structure. So for that reason, you should not be using this formula for benzene, but you should know what it means in case you are reading older literature. Now, to understand bonding in benzene, we actually have to look at a number of other hydrocarbons with pi bonds before we can consider benzene, and we have to then compare electronic structure of benzene with those hydrocarbons. So when it comes to localized pi electrons originate from atomic p orbitals. So in the simplest molecule of ethene, two individual atomic p orbitals overlap to form bonding and anti-bonding molecular pi orbitals. And each carbon contributes one electron for bond formation. So molecular pi orbital is bonding. There is electron density between the two nuclei, and anti-bonding has a node between two nuclei. Obviously, bonding molecular orbital is lower in energy compared to starting atomic orbitals, and anti-bonding is higher. Since there are two electrons, one electron pair, that electron pair fits into lower energy orbital, and that's pi orbital. So that would be molecular orbital description of ordinary localized pi bonds. Now let's consider an alkene triene with delocalized electrons. And so what is molecular orbital description of 1,3,5 hexatriene? Well, on the left we have molecular orbitals of ethene, which we just covered. And then 1,3,5 hexatriene is shown on the right. There are 6 carbons that contribute 1 electron and 1 atomic p orbital each. That means that there are a total of 6 pi electrons and 6 pi bonds. 3 of those pi bonds will be bonding, 3 anti-bonding. So 3 will be lower in energy compared to original starting atomic orbitals, and 3 will be higher. Note that lowest energy orbital, pi 1, envelops the entire molecule. So electrons are clearly delocalized. So that shows electron delocalization. Entire molecule is enveloped. Then second orbital in the order of increasing energy, pi 2, has a node, a vertical node in the middle between carbons 3 and 4. So it still shows electron delocalization. And then highest energy bonding molecular orbital, that's HOMO, a highest occupied molecular orbital, pi 3, has 2 nodes, and they are between carbons 2 and 3 and 4 and 5. Note that pi 3 molecular orbital looks very much like valence bond formula of 1,3,5 hexatriene shown at the bottom. And that illustrates actually the weakness of valence bond formula, because valence bond formula actually represents only 1 pi orbital, and it is not capable of showing electron delocalization. And then you can see as energy increases, number of vertical nodes increases, and we end up eventually with completely antibonding pi6 orbital, which has a node in between each of the carbons. Since there are 6 electrons, there's 3 electron pairs. Those 3 electron pairs fill 3 bonding orbitals, while 3 antibonding orbitals are empty. So you can see how molecular orbital theory explains electron delocalization. It explains it by existence of orbitals such as pi1 and pi2. And also note how in an open chain compound with delocalized electrons, these orbitals stack up. So they stack up in energy, so each orbital is higher in energy compared to the previous one. And now we can consider molecular orbital description of bonding in benzene. Benzene forms a closed loop of delocalized electrons. So 3 pi bonds that are delocalized form a closed loop. To determine or to come up with energy levels, we have a useful mnemonic. And that mnemonic is that when delocalized electrons form a closed loop, a ring, then energy levels correspond to a polygon, to corners of a polygon that has same number of corners as there are atoms in the ring. So benzene has 6 atoms, 6 carbons in the ring. That means we should be looking at hexagon. And each corner of hexagon will correspond to energy level of 1 orbital. Of course, polygon has to point with 1 corner down. So when applying this mnemonic, make sure that polygon points with 1 corner down, not with a side down. So that allows us to determine relative energy levels of orbitals of benzene. They are labeled here as psi orbitals, not pi orbitals. So psi1 is the lowest energy orbital, and then psi2 and psi3 are degenerate. So note that two remaining bonding orbitals are degenerate. They are the same energy. And same goes for next 2 antibonding orbitals, psi4 and psi5. They are also degenerate. And then we have psi6, of course, highest energy antibonding orbital. Again, we have 3 electron pairs, 3 bonding electron pairs, and they fill psi1, psi2, and psi3 orbitals, bonding orbitals. Here is what those orbitals look like, looking from the top. So you can see that psi1 orbital envelops the entire molecule. And so that's donut, that's not as we represent as donut above and below the ring of electron density, the localization of electrons around the ring. And then psi2 and psi3 have vertical node. Again, this is view from the top. And so you can see there are 2 vertical nodes at 90 degrees to each other. One in psi2 orbital, the other one in psi3 orbital. And of course, as we go to other antibonding orbitals, there are more and more vertical nodes. Now we can compare molecular orbital description of bonding in 1,3,5-hexatriene and benzene. So open chain, compound, and closed loop of delocalized pi electrons. Both 1,3,5-hexatriene and benzene have delocalized electrons. They have the same number of delocalized electrons, but we have open chain versus closed loop. 1,3,5-hexatriene is rather unstable compound and highly reactive. The reason for it is in the small HOMO-LUMO gap, small gap between highest occupied and lowest unoccupied molecular orbital. As a result, 1,3,5-hexatriene is highly reactive because it can easily donate HOMO electron pair, or it can easily accept electrons into LUMO orbital. On the other hand, electronic configuration of benzene is completely different because psi2 and psi3 orbitals are degenerate, and same goes for psi4 and psi5. Psi2 and psi3 are lower in energy, and noticeably considerably lower in energy compared to pi3 orbital of 1,3,5-hexatriene. So HOMO orbital of benzene is much lower in energy compared to HOMO orbital of 1,3,5-hexatriene. And LUMO orbital of benzene, because psi4 and psi5 are also degenerate, is much higher in energy compared to LUMO orbital of 1,3,5-hexatriene. As a consequence, reactivity of benzene is rather low. Because of low-lying HOMO orbital or orbitals, benzene has very low tendency to donate its electron pair, And because of high energy LUMO orbital, benzene also has very low tendency to accept an electron pair. So for that reason, benzene is exceptionally stable for an unsaturated compound. Such molecules are called aromatic, and so benzene is a typical example of an aromatic molecule. And from analysis that we have done so far, we can see that molecule is aromatic if it is unsaturated, that means it has carbon-carbon double bonds, conjugated, so double bonds are conjugated, which means that double bonds are separated by a single bond, planar, so ring has to be planar or flat, so that electron delocalization is possible, and finally cyclic, so all the bonds, all the conjugated bonds have to form a ring. And so benzene satisfies all those requirements, so it's aromatic compound. Here, as an extension of previous discussion, we have shown how to determine energy levels of 4 and 5-membered rings with delocalized electrons. For 4-membered ring, you draw a square with one corner pointing down, and each corner represents one molecular orbital, molecular pi orbital. For 5-membered ring, you draw a pentagon with corner pointing down, and again, each corner represents energy level of one of the molecular orbitals. Finally, to summarize, we are going to very briefly look at molecular orbital and valence bond description of bonding in benzene. So molecular orbital theory describes benzene as its orbitals originating from original 6 atomic p orbitals that overlap to give rise to 6 molecular pi orbitals, and they are responsible for electron delocalization in benzene. Typically, this is shown pictorially as on the right in the molecular orbital theory box as donut of electron density above and below the plane of the ring. So that shows electron delocalization. Now you should know that this is only the lowest energy psi-1 molecular orbital of benzene. Valence bond theory represents electron delocalization in benzene by invoking concept of resonance. So it represents benzene as resonance hybrid of 2 individual Lewis structures with alternating double bonds. And so the actual structure of benzene is combination of the two, somewhere between the two. And again, final very important point to remind you, this is resonance arrow, so you should be able to use resonance arrow correctly and recognize it when you see it. It's single arrow, single double-headed arrow. Make sure that you don't mistake that for an equilibrium arrow and you don't use equilibrium arrow instead, because this is not an equilibrium. Resonance is not an equilibrium. It's a completely different concept. This completes introduction into electron delocalization and resonance. And next we are going to look into how to draw resonance structures and what is resonance hybrid.